In this video, we're going to prove the area of a circle using integration, okay? So imagine that you have a circle that has a radius of r, like how I've drawn here on your x and y axis, and it's got a center at the origin. Then we can say that the equation of this circle is x squared plus y squared equals r squared. And we're going to show that the area inside this circle is pi r squared, okay? So the way that I'm going to do this to make things simpler is I'm going to find only the area of the top right quadrant or the top right quarter of the circle, and then I'm going to times it by 4 at the end, okay? So I'm only looking right now for this area, and then I'm going to multiply it by 4 because it's a quarter of what we need, of course. So what I'm going to do is I'm going to integrate the function. So let's just rearrange x squared plus y squared equals r squared to get y on its own. So if we do that, then we have y squared equals r squared minus x squared, which means that y is plus or minus the square root of r squared minus x squared. But I'm not going to write plus or minus. I only care about the plus, because this function here, y equals the square root of r squared minus x squared, that's actually just going to give you the equation of a semicircle in the upper half of the plane. But I don't actually care about what's below. So I don't need any negative y coordinates on this circle because I'm only finding the 1/4 first, and then I'm timesing it by 4. So this is completely fine for now for what we're doing. And now we're going to try and integrate this function. So we're going to do the integral from 0 up to r, because that's the ending x coordinate, of the square root of r squared minus x squared, like this, dx. So now all we've got to do is work out how to actually integrate this. So it turns out the way that we're going to do this is actually by using a trigonometric substitution. Okay, I know that might sound a bit crazy, but it's the way to go. The reason why this works is because, remember, we have an identity that says that cos x squared plus sine squared x is always equal to 1. Okay, and that means that if I slightly rearrange one of them, let's take sine squared away from both sides, I've got that cos squared x is identical to 1 minus sine squared x. And so if I then times everything by r, or even better, r squared, then r squared cos squared x is identical to r squared minus r squared sine squared x. And actually, you might be able to notice that this is very similar to what we're trying to integrate, or at least the inside of the square root is looking very, very similar to that identity. So here's the idea. I'm going to make a substitution, and I'm going to say, let x be equal to r sine theta. And you're going to see basically that the yellow / orange working out is just going to kind of manifest itself. So first of all, let's just find what dx d theta is, just to make our lives a bit easier. That's going to be r cos theta. So that means that dx can be replaced by r cos theta d theta, which we'll do in a second. Going back to the integral, we've got the integral, and let's do the limits now as well, right? So when x is 0, that means that theta would also have to be 0. So our new limit in terms of theta at the bottom is 0. And when x is r, we get the equation r equals r sine theta, which means that sine theta is the number 1 if you divide both sides by r, which means that theta would be pi over 2. So our upper limit is pi over 2. Okay, so pi over 2. And then we're going to go in. So we've got the square root of r squared minus x squared, and x squared is r squared sine squared. And you can see why I've written that stuff in orange or in yellow earlier. And dx is going to be replaced by r cos theta d theta. Okay, so the reason why I've done that stuff in orange to show you what that really is now you can hopefully quite easily see how this is going to simplify, because r squared minus r squared sine squared x, or theta, can be replaced by r squared cos squared theta, and then I'm taking the square root of it. So the whole square rooted function is just going to be r cos theta. Okay, and then I've got another r cos theta here, so that is just going to get squared. So it's going to be r squared cos squared theta d theta like that. Now we're going to use another trig identity. We're going to use the double angle formula for cos. So cos of 2 theta is actually 2 cos squared theta minus 1. And I've used that because you can't directly integrate cos squared theta. It's not possible. You have to use an identity to do it. So rearranging this, we can see that actually cos squared theta is the same as a half plus a half cos 2 theta. And that's exactly what I'm going to replace cos squared with. So now I can write my integral as the integral from 0 to pi over 2 of r squared, and then open brackets, a half plus a half cos 2 theta. And we're almost ready to integrate it now. And that's d theta. Okay, so the last thing that I would like to do is I'm going to factor out an r squared over 2 from every term, just to keep everything nice and simple. You don't have to do this, but I like to. So now I've got 1 plus cos theta, hopefully, or cos 2 theta. Hopefully that makes sense what I've done there. I just think it's easier to integrate like this. Okay, and then this is equal to r squared over 2, and then now we can integrate. So the integral of the number 1 is theta, and the integral of cos 2 theta, let's think about that. It's definitely going to involve a sine 2 theta. It's definitely going to involve a 1/2. If you differentiate sine, you do get positive cos. So cos integrates to positive sine, so that will be a plus there. Hopefully that makes sense the way I've done that, because sometimes I get a bit muddled up as like, is the integral of cos sine or is it minus sine? Or, you know, sometimes even I can get a bit muddled up with that. So I'm like, I know it's going to be something times sine. Then I work out what the coefficient is. So it's a half. It's a half because if you differentiate sine 2 theta, a 2 will come out. So by integration being the opposite of differentiation, we need to do the opposite. So divide by the 1, divide by the 2, so times by a half. And then I've just thought about differentiation because I know that sine differentiates to cos, so I know that there needs to be a plus there. Okay, then moving on, I've got the integral from, oh, I've got the stuff, but I'm evaluating it from 0 to pi over 2. And then I can plug my values in. So I've got r squared over 2, and then here I've got pi over 2 plus 1/2 sine, this is 2 times pi over 2, so this is just pi, okay, minus r squared over 2 times, this is like 0 plus a half sine 0. Okay, and that second bracket is boring because it's just all zeros. And that's a 0, but I think I've written theta there, so that's a 0. Okay, then let's actually evaluate what each of these little bits are. So we've got r squared over 2, and then we've got pi over 2. Sine of pi is also 0, so that's just plus 0. And we've got minus r squared over 2 times another 0. 0 plus a half sine 0, that's just 0. So overall, we've got r squared times pi over 4, and that's it. And again, guys, this is a quarter of the circle's area. We have found only the top right quarter because it's easier than doing the whole thing in this form of integration. If you know about integration using polar coordinates, then it's a lot more doable, but I'm avoiding that in this video. So this is a quarter, so we should times the area by 4 to get the entire circle, because clearly all of the areas are the same. So that means that the area of a circle really is 4 times r squared pi over 4, which you can just write it as pi r squared because it gets rid of the 4. So that is the area of a circle using integration and why it's equal to pi r squared. Hopefully that was helpful. Thank you guys so much for watching. As always, please do feel free to like and subscribe if you enjoyed the video. And yeah, quick public service announcement. You'll never, ever, ever see a mid-roll ad on this YouTube channel because I do not believe that it's moral to put adverts in the middle of an educational video, basically. So if you ever see one, please do leave a comment and I'll come in and delete it because it was a mistake. Thank you so much for watching, and I'll see you in the next one. Cheers.